Hey everyone, welcome back to another School of Solana bonus lesson. Today we are talking about Pinocchio, a super minimalist Trust library that makes Solana program development a lot smoother. Unlike the big, heavy Solana program crate, Pinocchio keeps things lightweight and efficient, giving you great performance without sacrificing developer comfort. So let's dive into it.
Pinocchio is a zero-dependency Solana development library that allows developers to craft Solana programs without pulling in the heavyweight Solana program crate. It works by treating the incoming transaction payload, such as accounts instruction data, as a single byte slice and reads it in place using zero-copy techniques. For context, Anchor provides a macro-heavy approach that abstracts away many of the low-level details of Solana programming. Anchor uses 8-byte discriminators for instructions and accounts generated via a hash of their names, which helps with routing but consumes much more space. In contrast, Pinocchio uses single-byte discriminators, which is enough for up to 255 instructions. This smaller footprint is just one example of how Pinocchio prioritizes efficiency without sacrificing usability. The minimalist design of the Pinocchio unlocks several major benefits. Firstly, program uses fewer compute units, up to 30% less in typical scenarios, since there is no extra deserialization or memory copies happening behind the scenes. Second, the linear code path results in smaller binaries deployed on chain, often up to 70% smaller than Anchor equivalents. Third one, there is zero dependency drag because no external crates are to update or worry about breaking changes. While Anchor extracts away many details with macros, Pinocchio makes code more explicit. This transparency helps developers understand exactly what's happening, which is particularly valuable when optimizing for performance or addressing security concerns. So now let's hop to the performance comparison. Here we can see an example of implementation of SPL token using the Pinocchio and standard Solana program crate. As we can see on the screenshot, compute units used by the P token are up to 30 times smaller than the CU used by SPL token program. Now, let's look at some real-world comparison between Anchor and Pinocchio. Here we have a simple memo program implemented using both approaches. The Pinocchio version uses significantly fewer compute units, around 30% less. Even more impressive is the binary size reduction, with Pinocchio programs often being 50 to 70% smaller than their Anchor counterparts. Those efficiencies translate directly to lower transaction cost and improved throughput, which becomes critical at scale or for programs that need to operate within tight compute limits. For complex DeFi protocols or high-frequency NFT operations, these savings can make a substantial difference in user experience and operational costs. The Pinocchio ecosystem contains of core Pinocchio library and also includes specialized helpers like Pinocchio System and Pinocchio Token. This provides zero-copy helpers and CPI utilities for Solana's native system and SPL token programs. While Anchor provides an integrated ecosystem with its own CLI testing framework and ideal generation, Pinocchio takes a more modular approach. This allows developers to use only what they need and integrate with existing tools like Shenk for ideal generation. The design is extensible, allowing for additional program interfaces to be added as needed without bloating the core library. Now let's compare how programs are structured in Anchor versus Pinocchio. As we can see on the example, in Anchor, the program macro hides a lot of firing. It builds an 8-byte discriminator for every instruction and handles routing behind the scenes. Pinocchio, on the other hand, makes this pattern explicit. We start with the standard Solana entry point, receiving the program ID, accounts, and instruction data. From there, we use pattern matching to extract a single-byte discriminator and route to the appropriate handler. Each instruction implements try from to validate its inputs and the process method to execute the business logic. This explicit approach gives developers full control over how instructions are dispatched and processed, which can be leveraged for optimization or custom routing logic that would be difficult to achieve with Anchor's macro-based approach. Now let's take a look at how accounts and instructions are parsed in the Pinocchio. Account validation is handled very differently between Anchor and Pinocchio. Anchor uses attribute micros like account, mute, signer, and etc. to specify constraints, which are then checked at runtime through generated code. Pinocchio, on the other hand, uses Rust's try-from trait to explicitly validate accounts. This example shows how we validate accounts for a deposit instruction. We structure the accounts array, perform custom checks like verifying signers, and return a strongly typed struct. The Pinocchio approach is more verbose, but gives you complete visibility into what checks are being performed. This transparency is valuable for security audits and makes it easier to reason about edge cases or potential vulnerabilities. Also, there is no hidden magic, just standard Rust code that can be inspected and reasoned about directly. Now, finally, let's take a look at cross-program invocations. Cross-program invocations, also known as CPIs, show another stark contrast between Anchor and Pinocchio. Anchor uses a context-based approach that requires building account structures, creating a CPI context, and then calling the appropriate functions. Pinocchio streamlines this with a direct struct-based approach. You can simply create a struct with the required fields and call invoke. This example shows a transfer from owner to vault using the system program. The code is concise, yet explicit about what's happening. This direct approach not only reduces boilerplate, but also makes the code more readable and easier to audit. There's less indirection, which means fewer places for bugs to hide and a clearer path for security reviews. Now finally, let's take a look at security considerations. Security is a critical consideration for any Solana program, and Pinocchio's explicit approach offers significant advantages here. With Anchor, security checks are often hidden behind macros, which can make it harder to verify that all necessary validations are in place or to customize security logic for specific use cases. In Pinocchio, all security checks must be explicitly implemented. This includes owner verification to ensure accounts belong to the expected program, signer verification to confirm transaction authority, account size validation to prevent data corruption, PDA derivation validation to verify account addresses, and data structure validation to ensure data integrity. While this explicitness requires more code, it provides several security benefits. Auditors can easily trace all security checks without understanding macro expansions. Developers have full visibility into security boundaries. Custom security logic can be implemented without fighting framework abstractions. And finally, there is no risk of security checks being accidentally omitted due to misunderstood macro behavior. Now, let's hop to the hands-on example.
So let's implement our first Pinocchio program in an example of the vault. A vault allows users to securely store their assets. It is a fundamental building block in DeFi that at its core allows users to securely store their assets that only that same user can withdraw later. So let's start. Firstly, we'll have to be sure that Rust and Pinocchio are installed. Let's create a Rust workspace and add all needed dependencies. Then let's take a look at our program structure. Here we have our source code, cargo toml, where we also have to add create type to generate deployment artifacts later in target deploy folder. Then let's create a basic program template for our vault. First of all, we'll define that we will use no std crate for better performance using the Pinocchio. Then we'll define some program ID. For now, we'll use all twos. Then we should define our entry point function. It will be called process instruction. As its parameters, it would take program ID, accounts array, and instruction data. And it will return program result. For now, we'll just leave it as success result. Then we should not forget to add all needed dependencies. Then, as was discussed earlier, we have to announce our entry point using entry point macro. And then specify panic handler. For our demo, we'll use no std panic handler. Then let's jump to the defining our instructions. For it, we'll create a separate instructions module, which will include deposit and withdraw functionality. Let's start with implementing the deposit functionality. For it, we'll need to define our input structure, which will be called deposit, and it will contain all needed accounts that will be used for this instruction. And instruction data itself. Now let's add definition for our deposit accounts. As a part of the accounts that will be used in this instruction are vault owner account and vault account itself. For deposit instruction data, we'll have to specify how many lumpers we want to deposit. So it will be simple structure with only one field with amount. Now let's implement parsing and validation of the deposit instruction data. We'll do it by implementing try from trait that was discussed earlier in the lesson. So first of all, we'll have to check whether the data length is the same as the size of our amount. Otherwise, we'll have to return the invalid instruction data error. Then we'll try to parse the amount from the data. Also, we have to validate the input amounts for it to be greater than 0. If it will be 0, we'll have to return invalid instruction data error. Otherwise, we'll return our deposit instruction data structure initialized. Now we'll do the same validations for our deposit accounts. It will also implement try from trait. First of all, we'll have to check whether the number of account is enough. So we'll try to unparse both of these account infos and check whether the number of them is bigger than needed. So we'll take our first and second accounts, and possibly all other remaining accounts will be ignored here. If this check won't pass, then we'll just return program error. With not enough keys, program error. Then we'll add our validation check. For example, if the owner wants to deposit some number of Sol into the vault, he should be a signer of this instruction. So let's add this check. If the owner is not a signer, we'll have to return an error with missing required signature type. Then we have to check whether the vault is a system program. So we'll check whether it's owned by our Pinocchio system ID. If not, we'll return an invalid account owner error. Then we also have to check whether the vault is empty. If not, we won't be able to deposit there. And we'll also return invalid account data error. Finally, we have to check whether the proper vault account was provided to our instruction. Vault address should be PDA based on static vault seed and owner account address. So we'll have to check it manually. For it, we'll just calculate and find the proper program address for our seeds. For seeds, we'll be using vault as a static key and owner key as a second seed. Then we'll check whether the provided vault address and our calculated one are the same. If not, we'll have to return invalid account owner error. Otherwise, we can return all the accounts together. Finally, we'll do the same for the deposit structure itself. It will just combine both approaches for deserializing accounts and the instruction data. Then we'll add some process function which will execute this instruction and add all the business logic we need. For this, we'll also define it as tuple to be more readable. Secondly, when inside the function itself, in the implementation itself, we'll deserialize accounts, then we'll deserialize the instruction data. And then we'll return the deposit struct itself. Finally, we can add our own implementation for deposit. First of all, we'll have to define the discriminator to be able to parse the instructions that are provided to our program and correlate them with the needed instruction inside our program. This will be done based on the discriminator. In Anchor, discriminator is generated by the macro itself. Here we'll have to do it manually. For deposit instruction, we'll use 0 as a discriminator. Then finally we can add our function process, which will execute this instruction for us. And here we'll have our business logic for the instruction. Basically everything that happens in the deposit is transferring lamports from the owner to our vault. So let's add transfer instruction, which takes as the parameters from self accounts owner. We are transferring to vault, and the number of lamports is got from the instruction data amount. Then we have to invoke this instruction and return. Basically, we can return the result of the invoke transaction. Here we finally have all our deposit instruction implementations, so we can go through it. Basically, it consists of 3 parts. We'll go from up to bottom. Now, as we have defined discriminator for our instruction and the process function, we can utilize this in our entry point. Basically, what will happen here is we'll have to check the first byte of the instruction data that is used as the discriminator. So we'll go through using the match and we'll get the first byte of the instruction data. And if it correlates with our deposit discriminator, and also we have to get remaining data here. We can just call all our functions, first of all, which will be try from where we'll get all our needed data from the instruction data and accounts. And once this function succeeds, we can process it and the result will be returned for us. Then we'll also need to add default branch for our match statement, which will basically mean that we don't have this discriminator in the app and we doesn't support it, so we'll just return program error with invalid instruction data error. Basically what happens on the call to our program. Our program receives accounts and instruction data. It goes through the entry point, then we'll get the first byte of our instruction data. We'll check whether it correlates with our deposit discriminator, which is 0 for now. If it's true, we'll just get the data out of here, like the remaining instruction data bytes without the first one. Then we'll parse both data and accounts and process it. So basically it will parse all the accounts and all the instruction data and then execute our business logic of our instruction. And basically that's it. Now let's hop to the withdraw functionality. It will be basically very similar to our deposit, but will have more accounts and more checks to be able to withdraw the lampers from our Bolt account. So let's start by defining our withdraw structure. Because we want to withdraw something from the vault, we'll just withdraw everything, so we won't have any instruction data needed, we won't have any input params. So we'll just have to add our accounts here. Also let's add some discriminator logic here, so we won't forget about it later. For it, we'll use 1 as our discriminator. So what will be the accounts needed for our withdraw functionality? First of all, we'll need an account of our owner of the vault. Then we'll need an account of our vault itself. And then we'll need bump data for it. Then let's hop to implementing our try from trait to be able to parse and add all needed checks for our accounts. We'll also fix the typo here, and as usual type error will be mapped to our program error from the Pinocchio. So first of all, we'll gather our accounts from the account info structure, then we'll check whether the amount of them is proper or not. If it's not, we'll just return an error. Basically the same flow as for deposit. Then we also have to check whether the owner is the signer of this instruction. If not, we'll just return the same error for missing signer. Then we also have to make the same checks for Vault, whether it's owned by the Pinocchio system program and not some other unknown program. Then we'll have to check whether the Vault is not empty. We'll check it by comparing lamports that it contains to 0, and if it's true, then we'll return one more validation error. Then finally we'll validate that the address is properly cut from the PDA and the provided address matches the input address. And we'll fix the error here. And once we have all this implemented, we can, there's also some error. Yeah. Then finally we'll add our process implementation for our withdraw. Inside the process function, we'll create APDA signer seeds, which will be an array of seed from the static string, then account owner address, accounts owner key as ref, and then finally we'll add our BAMP to the seed to be able to sign the transfer instruction later. Then we'll define the signers for our CPI call, and it will be just one signer that will be created from seeds. to derive it here. And then we'll call transfer instruction that will be from self accounts vault to the vault owner, and number of lumpers will be basically everything that contains inside this vault. As this is CPI call, it basically means that the vault needs to sign the instruction. We'll have to call invoke signed and pass our signers to the instruction. And we'll have to do it like this here. Public function. And we'll have to return program result actually. That was the issue here. Then we'll add basically the same flow and to our process instruction function, and it will also check the discriminator, gather the data if needed, but here we don't have any data as an input, so we can just ignore it. And then we'll add our withdraw try from accounts and process it. And that's basically it. We can try to run it. We can try to build it using the cargo build SBF to see if we have any errors. Yeah, and actually we have some, so we'll have to go through and check what is wrong here. Into withdraw. Yeah, we are missing our implementation for withdraw that will unwrap all the needed accounts and create our structure so we can call process. So now we have it here, withdraw accounts, and that's it. Now we can try to check whether it's buildable one more time. Yeah, we're still having some issues. Instruction deposit. Yeah, just minor typos here, and basically that's it. Here under target deploy, we have our vault.so. It's basically simple binary that you can upload on chain and call it. As we can see here, there is no IDL being generated because it's not supported out of the box in the Pinocchio. But if you want, you can try using Shank. It's a library for generating IDLs. Or you can implement your own tests using pure Rust.
That is it for today. And as always, if you have any questions, feel free to ask on the Discord. Thank you for your attention and have a good day.